In the last few videos, you saw how I used my Electrify module to explore simple harmonic motion, uniform circular motion, and ultra-edge. Now it's time to take things up a notch. Today, we're going to analyze the Jarnebekov effect, also known as the tennis racket theorem and intermediate axis theorem. Let's see it in action. For this demonstration, we'll use this 2mm acrylic sheet as our test object. It's free to rotate around all three axes: the x-axis, y-axis, and z-axis. We'll attach the Electrify module to the sheet and capture the angular velocity along each axis. First of all, rotation around the z-axis. As the object spins and falls freely through the air, check out the graph of angular velocity. It's always positive. We'll ignore the part where it hits the ground and focus only on its free fall part. Next, we spin the object around the y-axis. The result is just like before. The angular velocity remains consistently positive during free fall. Now here's where things get exciting. Let's rotate the object around the x-axis. What's happening? The angular velocity doesn't stay positive. It switches direction, going negative too. Let's compare all three cases. Notice how, for the x-axis, the angular velocity flips between positive and negative, while the object is in midair. This behavior is not observed when rotating around the y-axis or z-axis. Why does this unique flipping occur only around the x-axis? The answer lies in the Jarnebekov effect. To understand it better, let's break it down with a visual model. Here's our test object. The global axes are stationary and fixed in space, while the local axes, which move with the object, are where the sensor measures angular velocity. When the object rotates around the y-axis, the moment of inertia is lowest because mass is distributed more closely to this axis. Spinning around the z-axis gives the highest moment of inertia. Finally, rotation around the x-axis falls in between. With an intermediate moment of inertia, and expected motion was like this. But according to the Jarnebekov effect, rotation around this intermediate axis is unstable, and slight disturbance to the rotation gets amplified, causing the object to flip. Let's see how local axis orientation changes with the rotation. Did you observe how the local x-axis inverts halfway through the rotation? That's the reason for the change in angular velocity direction, and that's why this phenomenon is so captivating. You can observe the same behavior with a tennis racket, which is why it is also known as the tennis racket theorem. Here's a fun challenge for you. Try observing the Jarnebekov effect with your mobile phone. That's all for this video. If you enjoyed learning about the Jarnebekov effect and have ideas for other experiments with Electrify, drop a comment below. Don't forget to like, share, and subscribe. See you in the next one.